So going back to our flash and our camera example, when you press the button to take your picture, it connects the switch to the lamp, to the little light bulb in there. It disconnects the capacitor from the battery and connects it across the resistance of, in this case, the lamp, the little light bulb in your camera. Well, the capacitor had charged. How much it charged to depends upon how long you had kept it attached to the battery, how long you waited for it to charge. So the capacitor has some initial value of charge. I'm going to call it Q naught. So Q naught is however much charge the capacitor comes in with. It could be that it was totally charged up. It may have just been partially charged. Doesn't really matter. Q naught is how much charge it does come in with. Well, when we connect the circuit here, there's nothing to force the charges to stay on the capacitor. The battery did that. The battery forced the charges to stay there. But when you disconnect the battery, there's nothing to keep the charges there, and so current flows. Basically, the capacitor discharges. So this is aptly named. It's a discharging circuit. Capacitor is discharging. As the charge leaves the plates of the capacitor, it's causing current to flow through the resistor. In this case, if we look at the charge on the capacitor as a function of time, it's going to start at a maximum value. As the capacitor discharges, that means the charge is leaving the capacitor. So the total amount of charge on the plates of the capacitor decreases with time. Now the capacitor cannot maintain this charge, this current forever. Quite honestly, it's usually a pretty short time. So the charge decreases, eventually reaches zero. What do you think the current looks like? The current's not going to stay constant because the capacitor can't continue to pump out the same amount of charge.
It's just a derivative, so it's just T as well.
Technically, if we look at this negative slope, it would be down here. I'm going to just draw the absolute value of it. So absolute value-wise, the current also starts with the maximum value and decreases to zero. So we look at the loop rule. There's no battery. All we have is the voltage drop across the capacitor and the voltage drop across the resistor. So those two added together have to be zero. So there's only two elements. So those two voltages added together have to be zero. That means whatever the voltage drop across the capacitor is at one instant in time, the resistor has the same voltage drop, just opposite in polarity, opposite in sign. So capacitor, remember, is Q over C for the voltage. Resistor is I times R. But I, we know, is dQ dt. So we end up with another differential equation. Again, we need a function for Q such that when we take the derivative of it, we get the same function back but a negative sign so they can add up to be zero. The charge as a function of time when the capacitor is discharging I'll leave it as tau. I did that in the last one. So Q naught being the original charge, e to the negative t over tau. Tau is still RC. This time it represents the amount of time it takes to drop down to 37% of its maximum value. But it's still a measure of how fast this is going to happen. The bigger the time constant, the longer it will take for the capacitor to discharge. The smaller the time constant, the shorter amount of time it will take to discharge. Current being the derivative of charge. Derivative of our charge will be negative Q naught over RC, e to the negative T over tau. When we solve problems mathematically, we tend to just ignore that minus sign. What meaning do you think that has?
It's just going the opposite
Right. When this capacitor was being charged, when it was connected to the battery, current was flowing this way through that branch. Now that it's discharging, the current's just flowing the other way. That's all that negative sign means. So we tend to leave the negative sign off when we're solving problems mathematically. We look at just the magnitude. What does this term represent? No. EMF doesn't show up in these equations because we're no longer attached to it. Number in front of your function. It's constant. It's a constant. What will it represent?
So it's charge divided by seconds.
Mm-hmm.
Maximum current.
It's a current. It is the maximum, yes. It's the maximum amount of current that will flow through our resistor, through the circuit. The types of questions we can ask with this are similar. How long will it take? Let's say we have a capacitor. Let's say we have our same capacitor and it was charged up to our 10 volts. So continuing on from the last example we did. This resistor though, if we go back to the example of a camera, the resistance of the light bulb is going to be a lot smaller. So I don't know what a real resistance will be for a typical light bulb. So I'm making one up.
Would the resistance value of a light bulb be related to its wattage?
The resistance, the wattage is related to its resistance.
So the lower the wattage, the higher the resistance, right?
Mm-hmm.
Since a
It
dimmer
lets
light
less current flows through it.
makes it not as
Not as bright.
bright.
So if our capacitance is 25 microfarads, let's say our capacitor was able to charge to the 10 volts. Our resistance is 20 ohms. How long will it take for the charge to drop to 1/3 of its original value? By the way, what is its original value?
12?
What units does Q have?
Coulombs.
Coulombs.
So divide the voltage, or multiply the voltage by capacitance.
Right. So our capacitance times our voltage would be 250 microcoulombs. Turns out that piece of information isn't actually necessary. I wanted to ask you that though, because a lot of people do mistakenly think that's Q. You can easily find Q from voltage, but the voltage is not Q. We want to know how long it's going to take for the charge to drop to 1/3 of its original value. That means we want the charge at whatever time we're looking at to be 1/3 of Q naught. That's what we want. You okay with that? Going over to our charge equation, going to put 1/3 Q naught in on the left side of the equation, because that's the charge at this time. That has to equal Q naught e to the negative t over tau. Doesn't matter what Q naught actually is, because the Q naughts cancel. And again, we already now have the exponential function isolated, so the natural log of both sides gets rid of our exponential function. So t is negative, tau comes over, tau is RC. So R is 20, C is 25 micro times the natural log of 1/3. Comes out to be 5.5 times 10 to the negative 4 seconds. So 0.55 milliseconds. Doesn't take any time at all. Very, 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 very quickly. And that's because the capacitor and resistor values are so small. So the time constant is very small.
Would it be the other way? Wouldn't it be 55 milliseconds?
No, because if you take your decimal place that way one more, you could go to 10 to the negative 5. You don't have to write it in terms of prefixes either, so you can leave it as your scientific notation.
550 microseconds.
Yes.
So if you were using that as a flash, your shutter would open. You could wait however long you want. The flash would flash and the shutter would close.
Mm-hmm.
And that's 1,820th of a second.
Doesn't take much time at all.
No, that's pretty.
So the equations, the new equations we have are the charge and current versus time equations. Please keep in mind these equations, the charge and current versus time is different if your circuit is charging versus discharging. These two equations right here are specific to a discharging circuit. The equations we did before were for the charging. So, how do you know if your circuit is charging or discharging? I guess is the first question.
Battery connected?
Bingo. If you have a battery connected. If you have a battery connected in the circuit with a capacitor, it's going to be charging. Capacitor cannot discharge as it's connected to the battery unless it was, say, charged the opposite polarity. We're not going to worry about that. We're assuming our capacitors were initially uncharged before they are connected to the battery. If you have a battery connected to your circuit, then your capacitor will be charging.
So the only thing that changes really is Qmax versus Q naught.
No, the other one is 1 minus e to the negative t over tau. The discharging is just e to the negative t over tau.
Oh yeah,
But yes, you also have Qmax versus Q naught. They certainly could be the same if you left the capacitor connected long enough to become completely charged by the battery. I just write it as Q naught because it doesn't necessarily have to be. completely charged.